Good morning and welcome to MAE 106, Lecture 7, using the rules of inference. My name is Richard Kohar, and today we'll be using those rules. Okay, so hopefully everyone can hear me. Good morning. Excellent. Yes. Excellent. Okay, so hopefully there's no glitches. In our previous lecture, this is the summary that we had. We had given propositions P, Q, and R. These are a tautology. This is a contradiction. We had gone through each of these rules: the idempotence, associativity, commutativity, distributivity, De Morgan, identity, domination, excluded middle, contradiction, and implication. So what we're going to do is we'll show that we can, given a proposition, we could show that something is equivalent. But one of the rules that we'll be using time and time again is the excluded middle. It's the we'll be using is the implication, which is the P implies Q is logically equivalent to not P or Q. And some people have a hard time with that. So our first example, or just kind of to illustrate how to use the implication rule. So we're going to apply the implication rule to, and let's use P or Q implies Q. Okay, so what we do is we're going to just apply the rule. We're going to have let's say P or Q implies Q. Okay, so using our implication rule, this is the rule that we'll be using. It's P implies Q is logically equivalent to not P or Q. But remember that P or Q can be any kind of proposition. It can be a prime proposition, a compound proposition. It can be anything. So in fact, this P could be a proposition that's a little bit more complicated. So for instance, over here, the P or Q could be considered a proposition. So what I'll do here is I will write this with a different color. So I'll call this R, just to illustrate this. So there's R. So what I'll say that this is logically equivalent to R implies Q. So just let R be P or Q. And then we can apply the implication rule, which says that if I have P implies Q, that's not P or Q. So let's use a light color. So there's kind of the first one, and there's the second. Right? So there's the R, and that's the P, and there's the Q. So what this tells me is that I need to think of this as R implies Q, which means then that I have not R or Q. So that's applying the implication rule. And then we can replace what we had for R originally. So we'll put the not P or Q or Q. Okay. So that's just how to apply or using the implication rule. So is everyone okay with that one? So if we apply the implication rule to, and let's just do a different one, which is P and Q implies R, the same idea. We're thinking really of this as kind of the P implies Q. This is what we're thinking. And again, what that rule keeps telling us is that it's that P, it's this first part here, that's the not, or the second part. So again, it's not P, so it's not this one. Or, which is what we have here, or the Q, and in this case it's the R. So now we're going to prove that not P implies Q is logically equivalent to P and not Q. Okay. So we start with the left-hand side of this. And we go through our list of rules that we could potentially use. The only rule at the moment where we have an implication is where we have this implication rule. The P implies Q is logically equivalent to not P or Q. So we'll apply it right there. So this is the implication rule, which is P implies Q is logically equivalent to not P or Q. So inside those brackets, I'll just put the not P or Q. So this is what we've done. I've just changed it. So then the next rule that we can apply, because I have to show that it's P and not Q, this is still a little bit more complicated. So what we could try is distributing this negative or this negation. And to do that, we have to go back to our rules here, and the one that handles the negative or the negation is De Morgan's law. So in this case, I apply the negation to the P, the negation to the V, which then turns it into an and we also apply the negation to the Q. So that's what we'll do here. So this is by De Morgan. So De Morgan's is that not P or Q is logically equivalent to not P and not Q. So I'll distribute this. So I get not P the negation applied to the or becomes an and then I have the negation applied to the Q, so it becomes not Q. And now we're kind of stuck because I have one more rule that I need to add to this list here, which is also quite useful. And that is what we call the double negation. And in this case, that's where two negatives, so a double negative, is just the original proposition P. Now, of course, we could show this very quickly. Oops. So here's the double negation. So We can show that really quickly. So I have just one prime proposition, so it's true or false. The negation flips it from false to true. And then I flip this again with the second negation, so this becomes true, false. And so these have the same truth values, which means that not P is logically equivalent to P. So, going back to this, this can get simplified. So the not P is logically equivalent to P and not Q. Okay, and so what we have, we can stop because we've reached the right-hand side of the equivalence. Again, there's my end of the proof. And so it was just 3 steps. We applied the implication to it. We then distributed the negative, which was using De Morgan's law. And then using the double negation, we were able to simplify the not P to just P and got what we were looking for, which was P and not Q. Okay. Is there any questions about that? Okay. So we just went in a circle. I don't know what you mean by a circle, because what we had shown is that we had the not P implies Q is logically equivalent to P and not Q. So what was nice about this was that using our rules, or the rules of inference, by applying the implication, the De Morgan, and the double negation, I was able to show that. Why not do a truth table? We can do it with a truth table. So just using Stephanie's suggestion, we'll do it by a truth table. So that left-hand side, well, we have two prime propositions, or we have P and Q. We'll do the P implies Q. We'll do the not P implies Q. And then we'll do the right-hand side. So this will give us the left-hand side here. We'll do the not P, then we'll do the not P or Q. And then lastly, we'll do the not not P or Q. So we'll have 4 lines. There's my implication. And then I just flip the values. Again, I flip the values for this. I have the not P or Q, so we know that I didn't step in poison ivy, but I got a rash. This is true. Didn't step in poison ivy, and I didn't get a rash. This is true. And this is true and true, so that's true. True implies, and this is false. No, I must have made a mistake. So I stepped in poison ivy and I got a rash. This is true. I didn't step in poison ivy. Okay. I didn't step in poison ivy. Oh, sorry. Where did the first not? Sorry, where did the first not come from on the right side in the first step? Like the step where it goes. Oh, just a second. You're doing ors, yes. The second one? Yes. No, I know. Sorry, I'm just answering Jack's question. He says, where did the first not come from on the right-hand side of the first step? Well, because so I'm working from the left-hand side, and well, I'm not really looking at this right-hand side yet. What I'm doing is I'm manipulating this left-hand side until I get to the right-hand side. Okay, so there's where that not comes from. This is the not and this is the not, but this P implies Q is changed using the implication rule. So it becomes P implies Q becomes the not P or Q. And then from there, I distribute this negative, which becomes not P and not Q. And then finally, I can simplify it. So that I got not P is P. And so I got P and not Q, which is the right-hand side. So you basically take the not from the left hand side. Yes, because I'm working with the left-hand side. So I don't really, what I'm trying to get is to this right-hand side, and I'm working and manipulating this left-hand side until I get to the right-hand side. So I apply these rules, and I do. Okay. Okay, so now doing this one. So this is an or. Thank you. Not P or Q. So let's cover this up. There we go. So with the or, I need to have at least one of them to be true. So I have false or true is true. False or false, this is false. True or true, This is true, and true or false is true. Okay. And lastly, we then flip, because we take this column and we'll apply the negation to it. So we'll go false, true, false, false. And this is the column that we want to look at. This is the right-hand side. Over here is the left-hand side. These are the same truth values. So therefore, not P implies Q is logically equivalent to not P or Q but that's not very helpful for us. So what we have done there is we did that first line right there. But really what we should have done is done the P and not Q. So let's do that. Okay. And the last one, we'll use this not Q and P. So it needs to be both of them to be true. Yes. There we go. So the second T is T. Okay, yes, the not Q should be T. Yes, so it should be false, true, false, true. And now I do the P and Q. So this is the true here. This is false and false, so this is false. And I also have false and true, which is then false. So now I can actually make sure that those are matching. There we go. And these are the same. So therefore, now by the truth table, we had shown that the not P implies Q is logically equivalent to P and not Q. Okay. Let's do another example. Right, so somebody asked me, there was a good question, which is, for the test, will we be allowed a formula sheet? I'm not sure yet. I have to discuss this with the other instructors. In the past, there have been formula sheets, and then also in the past, there haven't been any formula sheets. But I would say practicing it without the formula sheet is also important. The reason for that is because you might run out of time on the test. Okay. So I'm going to start with the left-hand side. So starting with the left-hand side, I have P and Q implies P. And what I'm going to do is I'm going to apply the implication rule. So just I'll just put this in a little different color. So remember, our implication rule is P implies Q is not P or Q. So in this case, the P is the P and Q, so it's not P and Q. No, you don't always have to start with the implication rule. It depends on what the proposition that you're trying to show is equivalent to. Okay, so in this case, we've handled that, the not P, or in this case, the Q is the P, so or P. So this is implication rule. Then I can apply De Morgan. So distributing this negative. So I get not P or not Q. Or the P, so this is De Morgan. Let's see, what could I do next to make this quick? What I'm going to do is I'm going to use the associativity rule. So the associativity rule is because I have an or and an or here, sorry. No, I won't use the associativity. What I will use is the commutativity. What I'll do is I'll treat this as 1. So this is one proposition, and here's the P, and I can change the order. So I'll do this. I'll do the P or not P or not Q. So all I've done is I've just changed the order. So this is the commutativity. Okay. And why I'm doing this is because you'll see in a second I have the or and the or, and because I have the same operation, I can move these brackets. So instead now I can write P or not P or not Q. And this is by the associativity. Because remember, I'm trying to get to a tautology. And we can see that this immediately, by the P or not P, that is a tautology. That was our example that we used for a tautology, but that's also the rule of the excluded middle. Okay, and the last rule that we have to apply is the domination rule. So P or tautology is logically equivalent to a tautology. If I wanted to be strictly following that rule, I would again write it like this. This is the commutativity. But I will just kind of put this in a cloud. And so by the domination rule, we know that that is equivalent to a tautology. And so we're done. We're done proving that P and Q implies P is a tautology. How do you pick which rule to use? That is a good question. Just some tips. There is no way really to know which rule to pick because this is part of the proof. So again, if there's to get rid of the implications, use the implication rule. If there's some negatives or negations, use De Morgan. And it really becomes kind of juggling or moving things around so that things kind of fall into place. We might get stuck, but that's part of the interesting part of the proof. That's what makes it a challenge. So, but these are some kind of helpful hints. Do you have to use this, or do we get an option to use truth tables for a test? So on the test, you'll have to do both. Okay, so you will have to use both. Let's do another one. Let's try. Okay, so let's try doing this proof. So what we have, we'll start with the left-hand side. So I'll just copy this out. I know that I have two implications, so I'm going to get rid of them one at a time. So I will start out with the inside bracket. So this is going to be not Q or R. This is in the implication. I'm going to do the same thing again on this one. So again, this is my P, here's my Q. So I know down here this should be the not P or not Q, should be Q. So this will be the not P, or over here is my Q, so I'll just copy this down again, not Q or R. So that's the implication again. And I need to get back to P and Q implies R, so I will shift these brackets because I need to get back to something like P and Q, so I'm going to try to get those kind of grouped together. So I'll shift those brackets so I get the not P or not Q, and there's There's my brackets, and this is done by the associativity. And what I need to do is I need to convert this part here and this into an implication. What I'm going to do though, because I don't have like a negative in front here, I'm going to do kind of the De Morgan's law again, so I can pull out those negatives. So going back to our rules, I have De Morgan over here, which is not P or not Q, and that's logically equivalent to not P and Q. So let me just put that. Right? So in this case over here, this then turns into P and Q, or R, and this is by De Morgan. Again, you can think of this as my not P or Q. And we know then that we can convert this back using our implication rule. So it actually can go one way or the other. So it doesn't matter. That's why we have this bicondition, this logical equivalence. So the implication, like I was saying, P implies Q is logically equivalent to not P or Q. I have this, which means I can rewrite it as P implies Q. So there's P implies Q. So that is P implies Q. So we did from the left-hand side, we did the implication, an associativity, a De Morgan, and then another implication, and we get to the right-hand side. And so therefore, what we have shown is that P implies Q implies R is logically equivalent to P and Q implies R. Okay. I just wanted to announce that I'll have office hours starting at 7 p.m. We'll do it over Zoom, and there's a link available through the Moodle page. And the homework is posted, and make sure you try out some of those questions. If there's any concerns, feel free to email me or ask those questions during office hours tonight. There's not any more questions. We'll sign off for today. Thank you everyone for tuning in and asking questions. Make sure, and of course, watching to make sure that I'm doing my truth tables correctly. Excellent. All right. Have a good day, everyone, and hopefully I'll see some of you tonight. Take care.